Okay, so let's start today's seminar talk. Okay, good morning to everyone. So today, first speaker is the Professor Kyung-Seok Lee, University of Miami. The title is the derived categories and the motifs of modular spaces of vector bundles on curves. Please start.
Okay, thank you very much. Thank you very much for introduction and the invitation. So it's my great pleasure to give a talk here. So today I'm going to talk about derived categories and motifs of moduli spaces of vector bundles on curve. So this talk is based on several joint works with Rane Biswas and Thomas Gomez and Han-Bon Moon and Professor M.S. Narasimhan. Okay, so let me start. So in this talk, C will be a smooth projective curve of genus greater than or equal to 2, and let M be the moduli space of, so in this notation MRN L to be moduli space of rank R stable vector bundles on C, whose determinants are isomorphic to a fixed line bundle L of degree D on C. And when R and D are co-prime, it is well known that there exists a Poincare bundle on C times M. So there's a bundle on C times M, and I can define so-called a Priamukkai transform from derived category of C to derived category of M, whose kernel is this Poincare bundle. So I can define this functor from derived category of curve to derived category of moduli space of vector bundle, and define this way. So I mean, I have an object in derived category. So let F be an object in derived category of C. Then I pull back F to the C times M and tensor with this Poincare bundle, and then push forward this object to this derived category of moduli space. So in this way, I can construct this Priamukkai transform, and and then I mean, so it gives a natural functor from derived category of curve to derived category of this moduli space. So then a natural question is whether this functor is fully faithful or not. So for length, when R is equal 2 and degree equal 1, so I mean, when R equal 2 and degree is 1, then Narasimhan and independently Fonarev and Kuznetsov proved that the derived category of curve can be embedded into derived category of this moduli space via this Priamukkai transform. So Fonarev and Kuznetsov proved this for when C is hyperelliptic curve, and then generalize this to general curve by some deformation argument. And Narasimhan proved this for all curves using so-called Hackett transformation. And then via similar argument, the above theorem can be generalized to higher rank case. So Bellman and Mukhopadhyay proved that when rank is greater than or equal to 3 and degree D equal 1, so degree is 1, then they prove that the derived category of curve can be embedded into this moduli space via Priamukkai transform. And there is condition. So I mean, for this to be whole, I mean, so then there's condition that this genus should be greater than or equal to R plus 3. And recently, Han-Bon Moon and myself generalized this to arbitrary D. I mean, for any R greater than or equal to 2 and D co-prime case, so we prove similar result. So the derived category of curve can be embedded into derived category of M via this Priamukkai transform. And we use a technique of parabolic bundles to prove this result. So I mean, the basic idea of proof is just using, I mean, the famous Bondar and Orloff's criterion. So the Bondar and Orloff criterion says that when X and Y are two smooth projective variety and E be an object in derived category of X times Y, then Priamukkai transform is fully faithful if and only if for any two close point X, Y in X, we have the following identities. So for example, when X is equal to Y, then the home between image, the home between image should be C when X is equal to Y and I equal 0. And when X is different from Y, then the home should be 0. And even if X equal to Y, this home between image should be 0 when I is negative or I is greater than dimension X. So anyway, the idea is just to check fully faithfully for skyscraper shift. Then one can check that the functor is fully faithful. It is enough to check this only for skyscraper shifts. Okay, so then in our case, so E is Poincare bundle, and then the image of Poincare bundle, I will call this image of Poincare bundle to be this EX. So yeah, so this EX is just to, I have a Poincare bundle on C times M, and this EX is just, I choose a point in C, and then I have a slice in X times this C times M. So EX is just a restriction of this Poincare bundle to this slice. And it is exactly the image of this skyscraper shape. Then, this Bondar and Orloff criterion actually reduced to prove the following three identity. So for point in C, then the home between this EX and EX is C. And for X in C, then the X between EX and EX is 0 for every I greater than or equal to 2. And when X is different from Y, then this home between EX and EY is 0 for every I. So, proving this fully faithfully is just reduced to this, compute this cohomology group. And there are various techniques to prove this cohomology. For example, as I told you, Narasimhan used Hackett correspondence, and Fonareff and Kuznetsov use explicit description of moduli space by, this description of Bossor and Desar and Ramanan to compute this one. And Beman and Mukhopadhyay, and we also, Beman and Mukhopadhyay use quite similar strategy with Narasimhan, and we use kind of a technique of parabolic bundle. So anyway, yeah, there are various methods to compute this cohomology, and anyone can obtain this result by just computing this cohomology group. So, is there any question? Okay, if not, let me keep going. So, but can you hear me? May I ask you? Can you hear?
Yeah, I can hear your voice very well.
Okay. Thank you very much. Thank you. Okay, let me then go further on. So anyway, we proved that the derived category of curve can be embedded into derived category of this moduli space. Then this image, how can I say, makes the so-called semi-orthogonal decomposition of the derived category of moduli space. So let me explain what is semi-orthogonal decomposition. So let T be a triangulate category. Then a semi-orthogonal decomposition of T is a sequence of four triangulated subcategories A1 to AN satisfying the following property. So first, there is no home from back to forth. There's no home from this small ai to small aj. For any small ai belongs to a large ai, and small aj belongs to large aj when I is greater than j. So when I consider this sequence, then there's no home from back to forth. This is first condition. And the second condition is just this A1, the smallest triangulated subcategory of T containing all these subcategories T. In other words, this A1 to AN generates this whole triangulate category. And in this case, we write T is equal to A1 to AL to denote T admits this semi-orthogonal decomposition. And there are several ways to interpret what is semi-orthogonal decomposition, and some people regard this semi-orthogonal decomposition as a non-commutative motivic decomposition. And I will anyway show you there are some parallel story with the motivic decomposition, actual motivic decomposition of moduli space. Okay, so anyway, we prove that there's at least one copy. I mean, for any Rn, for any Rn degree with a certain condition, we prove that there's at least one component of curve in the derived category of this moduli space. And then, it is a very natural question to ask what will be the full semi-orthogonal decomposition of this moduli space should look like. So then Professor Narasimhan made this conjecture, and independently Bellman, Garkin, and Mukhopadhyay state this conjecture. So the derived category of this moduli space is when rank is 2 and degree is 1, then they conjecture that the derived category of M should have the following semi-orthogonal decomposition. So what they conjecture is there must be 2 copies of points and 2 copies of curve and 2 copies of second symmetric product of curve, and keep going, and 2 copies of this G-2 symmetric product of curve, and 1 copy of G-1 symmetric product of curve. So they conjecture that the derived category of moduli space of rank 2, vector bundles of rank 2, and the determinant L should looks like this one. So the above conjecture is true when G is equal to 2 due to a famous theorem of Bondar and Orloff. Indeed, they found some semi-orthogonal decomposition of intersection of 2 quadric, and when genus is equal to 2, then moduli space is isomorphic to 2 4-dimensional intersection of quadrics in P5. So it follows that the derived category of moduli space has the expected decomposition. Of course, Bondar and Orloff's theorem is much earlier than this conjecture, but anyway, this gives the support on evidence for this conjecture. Okay, I will discuss recent development about this conjecture later, but how can I say? Let's first assume that there might be some decomposition like this. And then Narasimhan asked that, can he further decompose the above conjectural decomposition? So, if this moduli space have this decomposition, then it is quite a natural question, I guess. So can each component can be decomposed further or not? Okay, so Biswas, Gomez, and myself thought that when K is from 1 to G-1, then this K symmetric product will not admit a non-trivial semi-orthogonal decomposition. We think that. Then how we can prove that? So the most classical, standard way to prove a derived category of variety, smooth projective variety, does not admit to a non-trivial semi-orthogonal decomposition is to look at its base locus of canonical divisor. So indeed, there's a famous theorem by Kawatani and Okawa. So when X is a smooth projective variety, and such that the base locus of canonical divisor finite set, then they prove that the derived category of X does not admit the non-trivial semi-orthogonal decomposition. And they also prove that when S is a minimal smooth projective surface of general type with this global section of canonical divisor is greater than 1, then they also, this base locus of this canonical divisor, it has negative intersection. For any one-dimensional connected component of G, the intersection matrix is negative definite. Then they prove that the derived category of this surface does not admit the non-trivial semi-orthogonal decomposition. So being motivated by this theorem, Biswas and Gomez and myself proved that when K is from 1 to G-1, then we can explicitly describe this base locus of canonical divisor of K symmetric product of curve. So, so when when I consider this case, when k is in this range, 1 to g minus 1, then we prove that the base locus of canonical divisor of this K-symmetric product is exactly the locus, the points in this K-symmetric product, such that the global section of this divisor is greater than 1. So in other words, one can describe this locus in the following way. So we can consider Albanese map from this K-symmetric product to this Picard group, and then the base locus is exactly the locus where the Albanese map is not injected. So anyway, one can explicitly describe the locus where the base locus of this canonical divisor. Okay, then from this one, we can say something about indecomposability of this K-symmetric product of derived category of K-symmetric product of curve. So before this result, Okawa indeed proved that the derived category of curve does not admit a non-trivial semi-orthogonal decomposition. And besides Gomez and myself proved that when G is greater than or equal to 3, then the second symmetric product does not admit a non-trivial semi-orthogonal decomposition by the result of Kawatani and Okawa, the second result of Kawatani and Okawa. And we also proved that because, we explicitly describe this base locus of canonical divisor of K-symmetric product. So when K is greater than or equal to 1 and less than gonality, and this K-symmetric product, derived category of K-symmetric product does not admit a non-trivial semi-orthogonal decomposition. And later, Bastianelli and Bellman and Okawa and Ricorfi proved that when genus is exactly 4, then this third symmetric product does not admit a non-trivial semi-orthogonal decomposition. And they also developed some kind of a deformation of semi-orthogonal decomposition. And they proved that for when K is in this range, from 1 to this less than this G plus 3 over 2, then an integer part of this G plus 3 over 2, then they prove that this K-symmetric product does not admit a non-trivial semi-orthogonal decomposition. Because, the gonality for general curve is indeed this number, and they developed very nice decomposition and deformation theory. So yeah, they obtained this for arbitrary curve with arbitrary K-symmetric product of curve in this range. And then, as we saw, the base locus of a canonical divisor play an essential role in the study of SOD. But recently, Sun Lin studied some another kind of base locus, to study this non-triviality of this semi-orthogonal decomposition. So indeed, he studied the intersection of base locus of line bundles that are isomorphic to the canonical divisor in the Néron-Severi group. So he considered all all line bundle, which is isomorphic to this canonical divisor, but not linearly equivalent, but in Néron-Severi group equivalent. So then he considered the base locus of all these line bundle. And from this study, he proved that from this range, what we have done is almost half, but indeed he proved that when K is from this range, from 1 to G minus 1, actually this K-symmetric product does not admit a non-trivial semi-orthogonal decomposition. And he also proved that when the CI are curves of genus GI, which is greater than or equal to 2, and the AK are abelian varieties, then he proved that this product of this symmetric product of curves times abelian variety does not admit a non-trivial semi-orthogonal decomposition. Indeed, this result is somewhat expected by myself and Gomez, because by some reason I will explain later. But anyway, he found very nice. I mean, by studying this, base locus of these line bundles, he obtained this nice result. Okay, so any question so far? Okay, if not, let me, how can I say? So go back to this, this is semi-orthogonal composition. So I mean, so far we anyway have this conjecture, and we discuss. I mean, so anyway, there's this conjecture, and so I want to discuss about some evidence of this conjecture. So so in order to say that, let me discuss a little bit about motifs. So because motif is quite difficult notion for me, so let me briefly introduce what it is. So indeed, how can I say, the concept of motif was how can I say, developed by Grothendieck, because he wanted to understand the origin of common behaviors of different cohomology theory. So as far as I know, he developed the theory of ethyl cohomology and drum cohomology, and he wanted what is behind of these common behaviors of different cohomology theory. And he suggests the concept of motifs as follows. So one has a distinct impression that, I mean, so that each of these theory amount to the same thing. So I mean, so he formulate the notion of motif associated to an algebraic variety. By this term, he wanted to suggest that there's kind of common motif behind the similar behavior of different, very differently defined cohomology theory of algebraic variety. So in other words, so his suggestion can be summarized in the following diagram. So when K is a field, and this K is field of characteristic zero, then for every value cohomology, there might be some category of motif such that all value cohomology factors through this category of motif. So if this is true, then he thought that because all value cohomology factors through this mysterious category of motif, this explains why all these differently defined cohomology theory behave in a similar way. So that was his motivation. And indeed, suggested some version of motif. So let me, how can I discuss, some version of motif. So first motif I will discuss is so-called Grothendieck ring of varieties. So when K is an algebraically closed field of characteristic zero, and the variety to be the category of varieties of K, then the Grothendieck ring of varieties is just a ring generated by the symbol X, where X is an isomorphism class of the variety in this category of varieties. And this ring should be modular some relation. And the relation is whenever I have a closed subvariety in X, then this X is nothing but this sum of X a complement of G from X plus G. So I mean, when I consider this free abelian group generated by this variety and model out this by this relation, and then there's a very natural ring structure given by this product of variety. So this gives a ring, and this is called the Grothendieck ring of varieties. And there is another notion of motif which Grothendieck suggested and Manin developed it. So there's a notion of Char motif. So there is so first, in order to define Char motif, I consider this some category. So whose object is a smooth projective variety of K, and the morphism is just a Char group of this product of these two varieties. And then I take pseudo-abelian closure of this category. And so then this gives me so-called effective Char motifs. And then I invert left such motif to obtain the category of Char motifs. So this is the second motif, category of motif we will discuss. And there's another notion of, mixed motif, another notion of motif, so-called mixed motif. So in 1980s, Berlinson and Berlin independently made some conjecture. So, so Chow motif, for Chow motif, this deals only with the smooth projective variety, but they wanted to develop some theory which works for arbitrary scheme, singular and quasi-projective variety. So they also want to develop some theory which work in this setting. So they conjecture that there must be some abelian tensor category of mixed motif, containing this gross-index category of pure motifs as a full subcategory of a semi-simple object. And they conjecture that this has a structure of extension which recover the weighted grade pieces of algebraic case theory. So this is still a wide open conjecture, and there are many approaches, but I think nobody could construct this category of motif yet. But then Dellin suggests that, so this category is so hard to construct, so Dellin suggested to construct a derived category of this motif instead of constructing this itself. So then Hanamura and Levin and Voevodsky independently suggest the construction of this triangulated category of motifs independently. And it turns out that all these constructions are equivalent under some mild condition. So, so we will use Voevodsky's one to, in order to, describe this motif. So, so let this smooth correspondence be the category defined as follows. So the object is smooth scheme over K, and the morphism is the algebraic cycle G over this product such that each component is finite over X. Then one can check that this category is additive category, and the direct sum is given by this disjoint union, and the tensor product is given by product. And then he, consider this homotopy category, and then model out this category by these two relations. And then, so then he defined this triangular category of geometric motif by quotient of this homotopy category by this relation. And take this pseudo-abelian closure. So in any case, so he defined this triangulated category of geometric motif, and it anyway recovers, it, extends the theory of Chow motif. And so anyway, so there are, what I want to say is there are three, I'm sorry. So anyway, this category of motif has very nice property like finesse formula and homotopy invariance and Mayer-Biel-Torius sequence. And he also proved, Voevodsky also proved that this effective Chow motif is embedded into this triangular category of geometric motif. Okay, I discussed this three category of motifs in order to, discuss the motif of this moduli space. But I need one more setup because I will discuss the motif of stack. So I will need one more additional, additional technique. So there's so-called the dimensional completion of this motif. So I can, this is this coming from this theory of motivic integration. So I can give certain filtration on this gross-ending variety, for example, and then take a completion. And I can do the same thing for this, for this triangulated category of geometric motif. And also I can do the similar thing for Chow motif. So anyway, in short, there are three motifs I will discuss: this gross-ending varieties, or Chow motifs, or this Voevodsky's motif, and there are certain completions of these motifs. Okay, so is there any question so far? Okay, if not, let me keep going. So why I'm saying all these things? Because as I told you, we have a conjecture about derived category of moduli space of vector bundles on curves. So then, as I told you, so indeed Orloff conjectured that the derived category of coherent shifts and motifs of algebraic variety will be closely related. So we have a conjecture in derived category of this moduli space of vector bundles. So then it is natural to conjecture there must be a similar conjecture in the motive side. Indeed, so Orloff have the following conjecture. So when X and Y are two smooth projective variety having same derived category, then he conjectured that the motive of X is isomorphic to motive of Y. Here, the motive is Char motive with Q coefficient. And he also conjectured that when X and Y are two smooth projective variety and the derived category of X is embedded into derived category of Y, then he conjectured that the motive of X is embedded into the motive of Y in a sense. And also, Kuznetsov and Schindler gave a similar conjecture, kind of conjecture in the same spirit. So when X and Y are two smooth projective simply connected variety having the same equivalent derived category, then they conjecture that the difference between X and Y in the gross-ending ring of a variety times this Lefsetz this is affine class. This L is the class of affine line. So this difference between X and Y should give a multiple, this certain multiple of A1 should be 0. So so in this sense, people think that there must be some kind of parallel story. Between derived category of coherent shifts and the motive. So, okay, then the moduli space.
Can I ask you a question? Can I ask you a question? So if derived category of X sit inside derived category of Y already, and you also know that they have the same motive, does it imply that they are equivalent category? The derived category are the same?
I don't think so. So far, I think this is only conjectural level. So we can't say that. So of course, in that case, we can think this the orthogonal complement should be phantom.
Yeah.
But
but is phantom give you such example?
So as far as I know, there's no no example that this no example that certain the setting when you the setting what you say and there's a phantom orthogonal complement. I don't know any example of that kind.
So the phantom cannot see by the phantom cannot be seen in the motive neither.
So yeah, sorry, I don't know about that.
Okay.
So yeah, so people, logically there is what I can say is that there is a logical possibility of existence of phantom. But so far, all exceptional. Sorry, I think there can be an example. Sorry, because if I consider the surface of general type, then there are. I think there are some known cases that the charm motif of those surface have Lefsetz this. Some copy of this direct sum of Lefsetz motif. But there is a phantom. So I think I think there must be some example having surface of general type such that motif can be decomposed into Lefsetz motif, but there's phantom.
Okay, thanks.
But here in the the example I will tell you is all Fano, so I'm not sure there's an example in Fano case. But I think there is some example in the level in general type case. Thank you very much for the question. Yeah. So any other question? Okay, if not, let me go further. So in any case, the the motive of moduli space of rank 2 vector bundle is quite well known. Indeed, Bano computed this motif for rank 2 case using Thaddeus's work. So he proved that for any semi-simple category of motifs, there is the following isomorphism. And using his work, how can I say, and being motivated by the semi-orthogonal decomposition, I proved that indeed this decomposition can be written in this way. So this motif for any semi-simple category motif, the motif of moduli space can be decomposed in this way. This 2 copy of point, 2 copy of curve, 2 copy of G-2 symmetric product, and 1 copy of G-1 symmetric product. So any semi-simple category motif, we have this following decomposition. And so, I mean, Bano used Thaddeus Fleet to obtain this result, and we also, use Bano's work. So then we found a much simpler and conceptual way to obtain the same decomposition, but we need, we need to go to completion. So in order to obtain this result. So, for rank 2 and degree 1 case, for completion of this gross-ending ring of varieties or some completion of this Chow motif or Voevodsky's motif, we have the following identity. So the gross-ending ring of variety case, the class of motif can be decomposed in this way. Again, you can see that there are 2 copy of point, 2 copy of curve, and 2 copy of G-2 symmetric product of curve, and 1 copy of G-1 symmetric product of curve. And later, Bellman and Galkin and Mukhopadhyay obtain a similar decomposition in gross-ending ring of variety, not the completion. But they have some tojan. There is some possibility of having tojan. So they obtain similar decomposition in gross-ending ring of variety modular tojan. So, you already see some similar story. And using the same strategy, we can find the new decomposition for R equals 3 case. So for Gomez and myself, prove that when rank is 3 and D equal 1, then D equal 2 is same because it is just dual. So this class of moduli space of vector bundle can be decomposed into this way. So this, there are some copies of K1 symmetric product of curve times K2 symmetric product of curve. And this decomposition can be, there are this type of motivic decomposition. The formula is a little complicated, but anyway, one can obtain this one. And one can prove that the same identity holds in gross-ending ring of Chow motifs or gross-ending ring of Voevodsky's motif. So for the same, for this identity, so for the same identity in Chow motif, we use Bano's another work, computing this Poincare polynomial. And for Voevodsky's motif, there are some map from this gross-ending ring of variety to Voevodsky's motif. So we just apply this decomposition and map this to this ring by this map. And then, so anyway, the key idea of this proof is that we treat this motif with this motif of K-symmetric product when K is from 1 to G-1 as an irreducible, and the Jacobian as an irreducible term. So because we expected that this K-symmetric product and this product of this K-symmetric product and Jacobian will not admit a non-trivial semi-orthogonal decomposition. So indeed we, expect that and write it, and we found this, by this way we obtain this decomposition for rank 3 case. And Sunlin, indeed prove this. So actually this is Sunlin proved that this is the case. And we expect that for arbitrary rank R and this line bundle, indeed the motif can be decomposed in a similar way. And and then we go to the derived category world. So we expect that there will be some corresponding decomposition of derived category of this moduli space. And also we can conjecture this to be held in certain completion, but we expect that this to be held in the gross-ending ring of variety, for example, and the Chow motif and other motifs. And also we expect that by mirror symmetric consideration, we also expect that there might be some similar decomposition in Fukaya category or quantum cohomology of this moduli space. Okay, so any question so far? So if not, let me go further. So now let's go back to this semi-orthogonal decomposition of this moduli space. So recently, Professor Narashima and I proved that when length is 2 and degree equal 1 and C is non-high-quality curve and genus is greater than 16, then we prove that second symmetric product, derived category of second symmetric product can be embedded into this derived category of moduli space of vector bundles and curve. So indeed, we construct an explicit vector bundle F on C2 times M, and we prove that this Fourier-Mukai transform, whose kernel is F, gives this embedding. So then, I mean, this result automatically imply that this C2, the second symmetric product, become a parameter space of vector bundles on this moduli space of vector bundles on curve. Indeed, we construct functor from arbitrary, I mean, this case symmetric product to this derived category of case symmetric product to derived category of this moduli space. So, I mean, yeah. So the idea of construction is quite simple because, I mean, I have this diagram. So C times M. And I have this projection map. And then, yeah, we can, so there's, for each copy, C times M, there is a Poincare bundle. And then I pull back these Poincare bundle to here and tensor it. And then this vector bundle has a natural SK action. So, I mean, there's natural SK action on this CK times M. And then this bundle also is an equivariant vector, SK equivalent vector bundle, and gives an element here. Then, I mean, I have a semi-orthogonal decomposition in this way. So I can look at the image of this vector bundle here. And then one can check that this image can, I mean, the projection of this E to here gives an element. And then one can check that this element descends to here. And so we can, yeah, consider the Fourier-Mukai transform and ask whether it's fully faithful or not. So, and then we actually describe this bundle. And Narashima and I proved that when C is the curve satisfying our conjecture, our assumption, then we can explicitly compute cohomology. I mean, as we discussed, in order to prove a certain embedding, the essential part is compute this cohomology group, and we actually prove this cohomology using Hecke correspondence. So yeah, we prove this result. Okay, and we conjecture that okay, this functor, other functor also will give this fully faithful embedding. And I mean, we needed this assumption of non-high quality curve with genus greater than or equal to 6. Due to some technical condition, but we expected that this condition will not be, I mean, we do not need this condition, and the computation here will be the same for arbitrary curve with the genus greater than or equal to 2. And recently, there has been lots of progress in this direction. And yeah, Tebelev and Torres indeed studied. So indeed, in order to prove this result, we use Hecke correspondence. I mean, a lot, but yeah, there is another approach by Tebelev and Torres. So they studied this derived category of this modular space via tedious flip. So as we discussed, tedious flip is really provides strong tool to study this case. And they also use the work of Harf and Leistner and Ballard, Fabero, Kacharukov. The work of studying this variation of GIP and the derived category. So they obtain this theorem. So derived category of this modular space has the following semi-orthogonal decomposition. So they actually prove that the derived category has this decomposition. So this point G-2 symmetric product, G-2 symmetric product, and G-1 symmetric product. And as I told you, they how can I say, didn't prove that this is this generate the whole triangulate this whole category. So there is still remaining part. So it is expected that this orthogonal complement, conjectural orthogonal complement part is 0, but it's still, I mean, not known. And recently, again, very recently, both results are quite recent. I mean, yeah, 1 or 2 weeks before, as far as I remember. So they are all quite very recent result. So Su and Yao studied the derived category of this, again, saying derived category moduli stack of length 2 bundles with fixed determinant L on C, and they also obtain similar result. So they use this Borel-Weill theorem for loop group developed by Telemann, and the zeta stratification recently developed by Harpen and Eisner. So there has been lots of progress in this direction these days. Okay, any question so far?
So, may I ask a question?
Yeah, please.
So A is a phantom, can be phantom category?
Yeah, I think if A is non-trivial, then it should be phantom. But because I mean, from our motivic, how can I say, description. So this already cover whole Hodge diamond. So I mean, this part already occupy all Hodge diamond. So if A, there is something non-trivial A, then it must be phantom, I think. Yeah.
Thank you very much.
Yeah, welcome. Thank you.
And,
So,
and in the previous page, you mentioned a conjecture with the Professor Narasimhan.
yeah.
And what's the problem with the generalizing your results on rank 2 case to higher rank case?
So
I think technical problem.
I mean, I think it should be possible. I mean, for higher rank case, I mean, you mean for higher rank case when
yes.
this is, yeah, I think that should be possible. The problem is, I mean, to compute the bunch of cohomology groups. So I mean, so Professor Narasimhan and I use this Heck transformation, and I mean, this using this Heck transformation. I mean, it's not. I mean, it's quite complicated. It's already quite complicated to prove this anything. Okay. And Tebelev and Torres use this tedious flame, and this indeed I'm still reading their paper. So but it seems that they reduce lots of cohomology vanishing using this flip and this variation of GIT argument. So I'm trying to learn their technique to, I mean, come to. But I'm quite sure. I mean, this functor. I mean, indeed, yeah, Tebelev and Torres also define the functor. So I think that this functor and our functor should be equivalent. And then I think their technique, I think, should be also very. I mean, their technique is very strong. So I think maybe there's some chance to prove this embedding. Okay. I mean, for rank 3 case anyway, we have a very concrete conjecture. So maybe there's chance to prove this one.
Okay, thank you.
Thank you. So, okay, so yeah, and any other question? Okay, if not, this is just a report of recent development. And we believe that, I mean, so yeah, we believe that studying these derived categories and motif of this moduli space will shed some new light to this important classical subject. So let me discuss one example. So let me record the definition of ACM bundle or Ulrich bundle and Ulrich bundle. ACM is called arithmetic Cohen-Maclaurin bundle. So when V is a projective variety with ample line bundle zeta, then a vector bundle E on V is ACM if it doesn't have any middle cohomology. I mean, so I consider all twist with E with this zeta J, and I consider all middle cohomology, and if all middle cohomology vanishes, vanishes, then all mid-columns vanish, then I will call this an AGEA bundle. And an AGEA bundle is only if it satisfies this condition. I mean this E tensor theta inverse is zero. It has no global section, and this global section of E is rank times degree V. So these bundles play very important role in the theory of vector bundles on higher dimensional algebraic variety. So this is very active area these days, in the study of vector bundles on higher dimensional algebraic variety. So it is, I think it's quite natural to ask whether this moduli space of vector bundles admit a non-trivial AGEA bundle on it. And using some technique developed it so far, so Hanbom and I proved that when R is greater than or equal to 2 and D is cofine, then we proved that this EX, which was the image of skyscraper shape via this Fourier transform by Poincare bundle, or just a restriction of Poincare bundle on this slide. We proved that this is an AGEA bundle on this moduli space with respect to theta. We proved this for every rank and degree, but there's condition that G is greater than or equal to 3. So yeah, so we can prove this. We can prove that anyway. There's some non-trivial family of AGEA bundles on this moduli space, and we think this. We can check that this EX is AGEA, but not only in general. And when R is, so I didn't say anything about genus equal 2, but when rank is 2, then we can check that EX is indeed AGEA, and we conjecture that the above result is true even when genus is 2. And I think there must be many other application and interesting open problem. So I hope to report some new results in near future. Okay, thank you very much.
Okay, thank you very much for nice talks.
Thank you.
So,
Thank you.
any questions or comments? Okay, if not, then maybe let me ask you one question. So what happening in this derived category in the moduli? What happened D of CG? Because only happen until CG minus 1.
Right. So for CG case, there's again this Albanese map to Jacobian, and it's subjective. So this Albanese map indeed induce a non-trivial semi-orthogonal decomposition of this symmetric product of this G-symmetric product of curve indeed have a semi-orthogonal decomposition, non-trivial semi-orthogonal decomposition. So we can only expect this indecomposability from 1 to G minus 1. But from G, there is a semi-orthogonal decomposition, and this semi-orthogonal decomposition was described by Toda. Indeed.
I see.
Toda, and also I think Professor Leung and his colleague also described. I mean, there are several groups to describe this semi-orthogonal decomposition of this G. From G, there are semi-orthogonal decomposition always. Yeah.
Also, until CG minus 2, there are 2 parts, but CG minus 1 has only 1 part. Is there some reason to why?
Yeah, it's so when you see this Hodge diamond, when you see this Hodge diamond, so for example, the curve case, the component of curve, and one can see that indeed this decomposition induces some decomposition of a Hodge diamond. So when you see this Hodge diamond, for example, curve case, there's 1 copy in the, if I draw this Hodge diamond, and 1 copy in above and 1 copy in below. So it goes in this way, but this G minus 1 symmetric product is exactly in the middle.
I see.
So there is some kind of symmetry between this
I see.
case and the case, but in middle there's only 1 copy. Yeah, it was very mysterious when indeed Professor Narasimhan and I discussed this decomposition, and he told me when we found this motivic decomposition, he was happy because finally we understand why there's one copy. So anyway, yeah, that's one reason I have in mind.
Okay, thank you.
Thank you.
Okay, other questions or comments?
So for higher rank vector bundle, do you have some expected motivic decomposition for the moduli space?
Yeah, I mean, for rank 3 case, anyway, we have this motivic decomposition. And we expect from rank, I think rank 4 and 5, this motivic decomposition should be somewhat decomposed by, for example, rank 4 case. I think there must be some decomposition by symmetric product of curve times symmetric product of curve, symmetric product of three copies of certain. I mean, for example, rank 3, you saw that there are symmetric product of curve times symmetric product of curve. For rank 4 case, I think this product of 3 such term. And also there must be some term associated with Jacobian. So I think there might be some decomposition in terms of this product of curve and the Jacobian. Yeah, that's the general expectation we have. For any rank R case, asymptotic decomposition should be something like symmetric product of curve times symmetric product of curve times something like that, and R-1's time.
Thank you very
Did
much.
I answer your question?
Yeah, thank you. Thank you very much.
Welcome. Thank you.
Excuse me. So, so you said that there is a surface of general type.
Yeah.
Which is motivically trivial, but contains phantom subcategory. So what is this surface?
I think yes. To be honest, I should check the reference, but I think Godot surface, for example, I mean, yeah, because as far as I remember, sorry, I forgot one important things. Sorry. So the motivic decomposition I told you is Q coefficient, Chow motif with Q coefficient.
Mm-hmm.
So for example, Godot surface, as far as I remember, the motivic decomposition has 11 components, 11 copy of certain left motif with Q coefficient, Chow motif with Q coefficient. But as we know, the derived category Godot surface has a phantom, quasi-phantom in there. So I think, yeah. And I think Barlow surface, there might be some similar things, but let me check the reference and is it okay? I send you some, if I found some references. I think there are some study about charm motif with Q coefficient of surface of general type with PG equal Q equals 0. Yeah. And it seems that there are, but the point is it's Q coefficient, so the Tozen is ignored in a sense. So yeah, as far as I remember, let me check the reference and yeah.
Thank you very much.
Thank you.
So can I ask another quick question? So you look at symmetric product of curve and modular space of bundle.
Yeah.
How about modular space of bundle of different rank? Are they the derived category related?
Modular space of a different rank, you mean?
Different rank, yes, yeah.
You mean rank 2 bundle and rank 3 bundle, something like that,
Example, right? Yeah.
I think maybe there are some relation, must be, because I mean, when I see this some kind of, this, like, can I be little heuristic? Right? I mean, if I consider some kind of, tedious is this variation of tedious flip by variation of GIT.
Yeah.
And I think some kind of unstable, I mean, this flip, then there must be some flip. And I think this some part at the center of flip maybe decomposing into some, for example, this derived category of this moduli space of, for example, rank 2 bundle times C, something like that. So I think if I consider this rank R vector bundle and run this tedious algorithm, I think the flipping center might be decomposed into some moduli space of lower rank bundles. So in that sense, there might be some relation. Yeah. But I don't know any systematic way to understand this. Yeah. Not yet, sorry. Yeah, I haven't think about it. Yeah.
Okay,
Thank you. Thank you. Yeah. Thank you very much.
Okay, other questions? Okay, if not, then let us thanks again for the nice talk to the speaker.
Thank you very much. Thank you.
So next talk will start 11:15.